So, this is Mastering Physics, Chapter 14, number 59, and the problem is this. A circular hoop of mass and mass M, capital M, and radius, capital R, is pivoted on an axle passing through one edge. So there's the axle, there's R, the total mass, capital M. So it's pivoted on an axle passing through one edge as shown in the figure. Find an expression for the frequency of small oscillations in terms of m, r, and constants g and pi. So the first thing we need to know to solve this problem is how a physical pendulum oscillates. So we've talked about a simple pendulum in class. So you take a bob, you take a mass, and you hang it from a string. And it oscillates about an equilibrium point, right? It oscillates because of gravity. Well, a physical pendulum, so this is a diagram that I borrowed straight from the text. A physical pendulum is some extended object that oscillates because you have it secured at some pivot point, and it oscillates due to the force of gravity about some pivot point. So it's an extended object, not just a string and a mass. So for this extended object, it can be shown that the acceleration, in this case the angular acceleration, is equal to the negative of mg, the weight, times L, where L is the distance between the pivot point and the center of mass, and all that is divided by I, which is the rotational inertia of the object. So all of that times theta. Now remember, the condition for simple harmonic motion was that the acceleration was equal to the negative and some constant times the displacement. We talked about that in class. So this satisfies that condition, and what that means, since this is the condition for simple harmonic motion, that the acceleration is proportional to the negative of the displacement, then that means that the angular frequency of the system, the angular frequency that it oscillates with, is equal to the square root of the constant multiplying the displacement, in this case the angle. So now we have the angular frequency of the system. Now to get the frequency of the system, we divide omega by 2 pi. So now you have 1 over 2 pi times the square root of mgl over I. Okay, so you say, well, what is L? Because we're talking about a hoop. We're not talking about this physical pendulum picture here. Well, in the case of the hoop, the distance between the pivot point, referred to as the axle here, and the center of mass, is R. So we can plug that in. 1 over 2 pi times the square root of mg r divided by I. But what is I? Okay. So what is I? Well, what is I? We'll come back to that. So we're going to have to use the parallel axis theorem to get I. And the parallel axis theorem says that if you take the rotational inertia about the center of mass plus m d squared, the distance from the center of mass to the new axis of rotation, and in this case, that's just r. So let's use the parallel axis theorem. ICM in this case is mr squared, and you can look that up in table 12.2 in your text, plus m, and this distance d is r squared in the case of our hoop. So if you add those things together, you get 2 mr squared. So going back to our equation from before, we had found the frequency. It was equal to 1 over 2 pi times the square root of mgr over I, which we found to be 2 mr squared. So now divide out m's. 1 over the r's go away. 1 over 2 pi times the square root of g over 2r. So that indeed is the expression for the frequency for small oscillations of our hoop. And does it depend on things we would expect? Well, let's see. If you go to the moon, it's not going to oscillate as quickly because g is going to be less. The force of gravity is going to be less. So you would get a smaller number of cycles per second. The frequency would decrease. So I expect these to be directly proportional, the frequency and the acceleration of gravity. This also tells me that the radius of the hoop and the frequency are inversely proportional. So what that means is that if the radius is bigger, if the object is bigger, it's going to take longer to oscillate. Less cycles per second, and that is also what I would expect. So the relationship here between frequency and the variables is predictable, and if you do the unit analysis, let's see, meters per second squared over meters, you get 1 over second squared. Square root of that is 1 over seconds, which indeed is hertz, which is the correct unit for frequency.